What is time? It's a question that has puzzled philosophers, scientists, and thinkers for centuries. Is time merely a measure of change, or does it hold a deeper significance in the fabric of our universe? As we navigate our daily lives, time seems constant and linear, yet science reveals that it is anything but simple. We will discuss the complexities of time, including the theories of Albert Einstein that significantly shaped our understanding of this fundamental aspect of the universe. Time is a concept that has been defined in various ways throughout history. Traditionally, time has been viewed as a linear progression from the past, through the present, and into the future. The ancient Greeks, for instance, distinguished between two types of time: chronos, which refers to chronological or sequential time, and kairos, representing a more qualitative, opportune time. In the realm of physics, Sir Isaac viewed time as absolute, flowing uniformly regardless of events occurring in the universe. This perspective remained dominant until the early 20th century when Albert Einstein introduced his theories of relativity. Einstein proposed that time is not a constant; instead, it is relative and can vary depending on speed and gravity. His famous equation, known to everyone, illustrates the connection between energy and mass, ultimately suggesting that time itself is intertwined with the very fabric of space. Understanding time in this way challenges our intuitive perception and invites us to rethink our place in the universe. It prompts us to consider how time shapes our experiences and influences our lives. Einstein's theory of special relativity reveals that time is not a fixed measurement and can vary depending on the observer's motion. According to this theory, the speed of light is the ultimate speed limit in the universe, and no object can exceed it. As an object approaches the speed of light, time slows down for that object. For example, astronauts aboard a spacecraft traveling close to light speed will age more slowly than their friends remaining on Earth. This demonstrates that time is not absolute but relative. Moreover, Einstein's ideas suggest that time is intertwined with space. Together, they form a four-dimensional structure known as a spacetime. This structure can warp under the influence of gravity, affecting the flow of time. The implications of special relativity revolutionized our understanding of how time and space operate. This perspective not only enhances our comprehension of the universe but also prompts us to question our daily experiences of time. Einstein's General Theory of Relativity expands on his earlier work by integrating gravity into the fabric of spacetime. According to this theory, massive objects like planets and stars warp the spacetime around them, creating a gravitational field that affects the passage of time. Near a massive body, time runs slower compared to areas with weaker gravitational pull. For example, time passes more slowly on the surface of the Earth than it does in space, away from gravitational influences. This phenomenon is known as gravitational time dilation. One of the most striking examples of this concept is found near black holes. The immense gravity of a black hole warps spacetime so dramatically that time almost comes to a standstill at its event horizon. For an observer far from the black hole, it would seem as though anything falling into it is frozen in time. The speed of light is precisely 299,792,458 meters per second. To put it into perspective, light could circle the entire Earth approximately 7.5 times in just 1 second. This makes light the fastest thing in the known universe, establishing it as the ultimate speed limit. But why can't we exceed this speed? As an object with mass approaches the speed of light, its energy requirements increase exponentially. For example, reaching 90% of light speed demands more than double the object's initial energy. At 99%, it requires roughly 7 times that energy. And at 99.9% of light speed, the energy needed rises dramatically, to about 22 times the starting amount. This rapid escalation happens because, according to Einstein's theory, mass and energy are intertwined. As speed increases, the object's effective mass grows as well, requiring even more energy to continue accelerating. To reach the speed of light itself, an object with mass would require an infinite amount of energy, an impossible requirement given the limits of any technology, current or future. This limit isn't just a theoretical barrier, it's embedded in the structure of space and time itself, defining the ultimate boundaries of what can and cannot achieve this extraordinary speed. Einstein's theory of general relativity reveals that time is not a constant, it can be influenced by gravity. In strong gravitational fields, such as near a black hole or even on Earth, time actually moves slower compared to areas with weaker gravitational pull. For example, GPS satellites orbiting the Earth experience less gravitational pull than we do on the surface. As a result, their onboard clocks tick slightly faster than those on the ground. To ensure accurate positioning, these satellites must be regularly adjusted to account for this difference, illustrating how gravity directly impacts the flow of time in our daily lives. This phenomenon highlights that our perception of time is deeply intertwined with the universe's structure, reminding us that time is not just a straightforward measurement but a dynamic aspect of reality shaped by the forces around us. Time on Earth is measured by a 24-hour day based on our planet's rotation. In comparison, a day on Mars, called a sol, lasts about 24 hours and 39 minutes, making it slightly longer than an Earth day. The Moon takes about 29.5 Earth days to complete a single rotation, resulting in a longer lunar day. On the Sun, measuring a day is challenging, but it rotates once every 25 days at the equator. Looking at other planets, Mercury has the shortest day, lasting about 58.6 Earth days, while Venus has an extremely slow rotation of around 243 Earth days, making its day longer than its year. Jupiter, on the other hand, spins rapidly, completing a rotation in just about 10 hours. These differences show how time varies across celestial bodies, highlighting our unique perspective of time on Earth. Time travel is one of the most fascinating concepts in human history. Frequently encountered in science fiction books and films, the question of whether it is physically possible is a subject of deep discussion. Albert Einstein's theory of relativity provides essential insights into how time works and lays the scientific groundwork for the idea of time travel. Time travel can be categorized into two main types: forward time travel and backward time travel. Forward time travel occurs when an object moves at a significant fraction of the speed of light, causing time to pass more slowly for that object compared to an observer on Earth. For instance, a spacecraft traveling close to the speed of light would experience less time than what passes on Earth. However, backward time travel remains largely in the realm of science fiction. Some theories suggest that passing through the event horizon of a black hole might allow for time travel to the past, but this idea has yet to be substantiated by evidence. The concept of time travel has inspired numerous works in popular culture. The A Back to the Future series explores the entertaining and thought-provoking aspects of time travel, while shows like Doctor Who delve into more complex and philosophical discussions about the nature of time. The scientific and philosophical dimensions of time travel raise some of humanity's deepest questions. If we could travel to the past, would we be able to change past events? What truly is the nature of time?